So let's also talk about hyperbolic equation. So in these equations we're dealing with, in this case we've already assumed we've taken an ODE, we've written the weak form, and now we've got it into a set of matrix equations. So here's your elasticity. So if this was a quasi-static problem, of course this would be 0. This is time derivative on displacement. Second, this is acceleration. Quasi-static, you just have k times displacement equals a force. Here we're including two things. One is dissipation. So if you have damping in your structure, and here is your acceleration and mass. We're going to subject this to initial conditions in displacement. Here's your initial velocity over a bar of length L. So this is defined over the whole domain. And what's often used to solve these transient problems is what's called a Newmark scheme for second order time derivatives. In this case, what I'm defining is U defines the whole set of displacement. So this is a vector of all your nodes. Imagine each one of these square points is a nodal solution of a bar of some length L. Here is displacements at the previous time step. So my subscript S is marching forward in time, one time step delta t. So here's your delta t time step. Here's your velocity, and here's your acceleration. So this gives displacement at the next time step. You get velocity at the next time step using the current velocity and acceleration times delta t at some intermediate time step, s plus alpha. The trick is you need to know acceleration at these intermediate steps for here s plus gamma and s plus alpha. So we're defining this acceleration at the intermediate time step as a weight. So basically you choose some theta as a weight and you average it at the current time step and the future time step. So one important thing is that alpha and gamma determine your stability and accuracy. Another way to think about these two equations are they're essentially a solution. Here's your linear order in delta t, and here's your second order in t squared and 1 over 2. So you could expand this out to even higher order if you knew higher order derivatives. Other important thing to note is if gamma is less than alpha and alpha is greater than 1/2, here's the stability requirement. So you can show that if delta t is less than a critical time step, which is based on your maximum eigenvalue and this difference in 1 over square root, then you have a stable solution. Now of course you may not know your max eigenvalue at the beginning, but that's usually where engineering judgment comes in. You can often start with some small delta t, or let's say you start with a large delta t and it's unstable, then you know you need to continue reducing this until you can get a stable solution. The final equation, what I'm showing here, is for a fully conserved bar that will vibrate for infinity. So it's a toy problem where there's no damping, no losses. You just have stiffness and inertia. And you can set this up, and depending on how big your mesh is, depends on how many of these modes that you can solve.